Okay, so before we get to our information about isotopes, let's do some quick review of atomic structure. So remember, when you look at the periodic table, the number in the upper left-hand corner is your atomic number, how many protons you have, and the number on the bottom is your atomic mass, and that number is a decimal. So your mass number is when you round the atomic mass to a whole number, and that is your number of protons plus your number of neutrons. So today, one thing we're going to explore is why the atomic mass is a decimal. So an isotope refers to atoms of the same element that have different masses. So they have the same number of protons and they have different number of neutrons. The protons is always going to be the same. Like carbon, for example, will always have 6 protons, but the number of neutrons and therefore the mass number can change. So that's what you're seeing here. 6 neutrons, 7 neutrons, 8 neutrons. A little bit more review. We talked about the isotope symbol. So this is just notation for when you're writing about isotopes. So we know that, like, for example, there are 3 isotopes of carbon, carbon-12, carbon-13, and 14. So the name, when you write it out, is the element dash the mass number. That's what the A is, mass number. So that's why when you see them written, you have it like that. The symbol, here you have a C and then a 6 and a 12. So remember, the letter is going to be your element. The number on the bottom is your atomic number, and the number on top is your mass number. So again, with isotopes, the whole thing is that you are going to have the same number of protons no matter what, because the element itself, the identity, is staying the same. And what is changing is the mass number, and that's because there are different numbers of neutrons. And we'll talk about how that affects things coming up. So you may be wondering, why do isotopes even exist? The short answer is that's just because that's how nature is. The long answer we'll go into a little bit shortly. So isotopes occur naturally. Most elements have at least one isotope, but some of those isotopes are going to be more common than others. We describe how common isotopes are by measuring the relative abundance or the percent distribution. So that number is a percent. The reason for that is because you can't count atoms, but there is a way, it's called mass spectrometry. I have a hard time with that word. And that allows you to calculate how common each isotope is. So for example, carbon, there are 3 naturally occurring isotopes of carbon. Carbon-12 is your most common at 98.9%. So 98.9% of the carbon atoms in nature are carbon-12. 1.1% carbon-13, and then carbon-14 is your least common at less than 0.1%. So ultimately, these percentages are important for understanding why the atomic mass on the periodic table is a decimal. So we'll go into that next. The atomic mass of an element is an average of the masses of different isotopes of the element, weighted by how common that isotope is in nature. So the atomic mass is what's called a weighted average. This can be a really difficult concept to wrap your head around. So if it's been confusing for you, try not to worry too much. It's hard. I'll try and make it as clear as I can through this explanation and example, though. So the equation for calculating atomic mass is like so. You have the atomic mass is equal to the mass of the isotope times its percent abundance. And then you do that for however many isotopes you have. Then the last step is to divide by 100, and that's because we're working with percentages. So it's important to understand the terms that are used in this equation so you can apply it correctly. So mass of an isotope, this is just like our mass number. So the mass of atoms is measured in atomic mass units, AMU. That comes from looking at how many protons and neutrons you have. So a proton is 1 AMU, and a neutron has a mass of 1 AMU as well. Electrons are so small that they essentially have 0 AMU. So what this number is, it's essentially your mass number of the isotope. It's the number of protons plus your number of neutrons. The percent abundance, again, that's a measure of how common the isotope is in nature. So here's an example calculation of atomic mass. Magnesium is what we're going to look at. So there are 3 naturally occurring isotopes of magnesium, and all of that is listed in this chart. So you have magnesium 24, magnesium 25, and magnesium 26. Remember, this is how we write out our isotope notation. This number here is your mass number. And then in the right column, it's telling you how abundant it is in nature. So the majority of the magnesium atoms in nature are going to be magnesium 24 at 79%. Magnesium 25, 10%, and magnesium 26 is 11. So we're going to take this information and plug it into our equation. So starting with our first isotope, we have magnesium 24. Again, this number is your mass number. So all you need to do is plug that in to the equation. And then you do the same thing with its percent abundance. So you can see how I've done that down here. Then you'll do that for however many isotopes you have. So we had magnesium 25 and magnesium 26. Then you do the math. Remember to do PEMDAS and do the math correctly. You want to do what's inside the parentheses first, and then you'll add those numbers together and divide by 100 because we're working with percentages. The number we get for magnesium is 24.32 AMU. Once you get that number, you want to check it with the number on the periodic table. So you can see we've done our math correctly because it is really close to what the periodic table says. So ultimately, that's why the number on the periodic table is a decimal, because it's showing the weighted average of the masses of all the different isotopes of an element. So to explain a little bit more what a weighted average is, if you imagine here, like magnesium 24, 25, 26, if we took an average of those 3 numbers, just a normal average, we do 24 plus 25 plus 26 and divide by 3, you would get 25. But that's not what we got for our weighted average calculation. The reason for that is because when you do a normal average, each number is contributing an equal amount to that overall calculation. When we do a weighted average, we're saying that some numbers are more important than others. So that's why this percent abundance matters, because we're saying we want this 24 to carry more weight than the 25 or the 26 because it's more common in nature. So whenever you do an atomic mass calculation, the number you get should always be the closest to whichever isotope is the most common in nature. So for this example, our most common one is magnesium 24. So that's why our atomic mass is closest to 24. Okay, so we've said that isotopes just occur naturally. And I said that was like the short answer to why they even exist. The longer answer has to do with stability, right? Not all possibilities of number of neutrons and protons actually exist. Only certain ones do. So you can think of isotopes as either being stable, unstable, or not even existing at all. So a stable isotope means it's going to stay together. An unstable isotope means it's going to fall apart. We also call those radioactive isotopes. And then the third category is like they can't even form to begin with. So whether or not a isotope is going to be stable is determined by the ratio of the number of protons to the number of neutrons. This matters because of the atomic forces within the nucleus. So remember, we talked about how there's the electrostatic force, which means the protons are repelling each other, and then the strong nuclear force between the protons and the neutrons, which are attracting. Ultimately, the reason why the protons don't all repel each other is because of the strong nuclear force. That is what is holding the nucleus together. But you have to have like the perfect ratio of protons to neutrons in order for that to happen. So our stable isotopes up here have that Goldilocks ratio. The unstable ones, the strong nuclear force isn't quite enough to keep it together because of how many neutrons to protons you have. And then if it can't exist, it means it's not even going to come together at all. You don't have the right number. You don't have the right ratio. All of this can be shown on the band of stability, which is a graph. So the graph shows us those different types of isotopes. Remember, whenever you're reading a graph, you always want to look at what's on the X and Y axis. So here we have the number of protons on the X axis and the number of neutrons on the Y axis. The line in the middle is just showing you what it would be if you had the same number of protons and neutrons. So like here, 65 protons, 65 neutrons. This line is not the data. It just helps us better understand this, which is the data. So let's zoom in on that. So here's our key. The squares are showing you the different types of isotopes. The dark square are going to be your stable isotopes. The gray ones are also maybe stable, but also maybe unstable. And then the white square are your radioactive isotopes, meaning the unstable ones. If it doesn't have a square, if it doesn't show up anywhere, it means that it is outside the band of stability. So this is the band of stability. And if you tried to make an isotope over here, it would not even exist, right? It is outside the band of stability, so it cannot even form. It does not have the right ratio of protons to neutrons. The last thing to look at here is a data trend. So whenever you're looking at a graph, you always want to be able to explain trends in the data. The way to identify a data trend is to look at the x-axis and be able to say what happens to the y-axis when the x-axis is changing. So here we can see as the number of protons is increasing, your number of neutrons is also increasing. But it's not happening at a one-to-one ratio, right? What's happening is that the higher up you get in your protons, the more and more and more neutrons are required in order to get a stable atom, right? That's like what you're seeing with the band of stability. These are stable atoms. So when it's only like 20 protons, all you really need is an equal number of neutrons. But once you get past 20 protons, you need more neutrons than protons in order to have a stable atom, right? So like if you look here, 60 protons, you need more than 60 neutrons. You actually need more like 82, 83 protons, or neutrons, sorry. So that's the overall trend, is that as the protons are increasing, a higher number of neutrons are actually going to be needed to keep that atom stable. And again, all of that has to do with the atomic forces and how the strong nuclear force is interacting with your electrostatic force. You can also see this on the periodic table. If you look at the first 20 elements, their atomic mass is like double their atomic number. But the further down on the periodic table, the higher those atomic masses are. All right, that's isotopes.